In this video, we're going to go over section 5.2 from our textbook, which is on more rational functions and their graphs. So first, let's let p of x and q of x be two polynomial functions. And for the rational function defined by p of x divided by q of x written in lowest terms, so fully simplified. And for real numbers a and b, we'll see that if our function gets bigger and bigger or approaches infinity as x approaches some number a, then the line x is equal to that number a is going to be a vertical asymptote of our function. And if our function approaches some number as x gets bigger and bigger, then the line y is equal to that number b is going to be a horizontal asymptote. So we'll see this more in this following example here, but vertical asymptotes occur where the denominator of a rational function approaches 0. And a rational function cannot cross this vertical asymptote because then we would be dividing by 0, which we know we cannot do. And then horizontal asymptotes occur when the x values get very large in the positive or negative direction, and we can cross these horizontal asymptotes. So let's go to this example here. We want to find the domain and the asymptotes of this graph here, where our function is in lowest terms. So it's fully simplified. So first we know that we're going to have a vertical asymptote where f of x is going to be undefined. And we know that f of x is undefined when we're going to divide by 0. Alright, so what we'll do is set our denominator equal to 0 and solve for x. This is a 5. So setting this equal to 0 and then factoring, we'll get 2x minus 1 and then x plus 3. Okay, so this tells us we're going to have two vertical asymptotes, one at x is equal to 1/2 and the other at x is equal to -3. And we get that by solving for x here, setting this equal to 0 and solving for x, and then setting this equal to 0 and solving for x. Similarly, since we know that when x is equal to 1/2 or -3, we're going to divide by 0, and we know that that will make our function undefined. This tells us that our domain is going to be all real numbers except those that make our function undefined, so -3 and 1/2. So in interval notation, we express that like this here. Alright, so this is our vertical asymptotes and our domain of our function. We also want to find our horizontal asymptote. So what we're going to do here, we're going to use the fact that functions of the form 1 over x get smaller and smaller as we let the absolute value of x get bigger. Alright, so in order to use this fact, what we first need to do is divide each term in our function by the variable of greatest degree. So what I mean is, our function f of x is given by this guy here, and we're going to divide each term here by the variable of highest degree. And looking at this guy, the variable of highest degree here is x squared. So we're going to divide everything by x squared. So we get that on the top. And this on the bottom here. Right, we can simplify this a little bit. Our first term here is going to be 1 over x because we can take an x out from the top and the bottom here. In the denominator, we'll get 2 plus 5 over x minus 3x squared. Alright, so what I mean is as x gets bigger and bigger, notice, for example, this 5 over x here. We let x get bigger and bigger. Let's say, for example, let's let x be 100. We'll start with that. We get 5 divided by 100, which is 0.05. Similarly, if we were to make x get bigger and bigger, so let's look at 10,000 now. Putting this into our calculator, we're going to get 0.0005. So as we increase this x value, as x gets bigger and bigger, then 5 divided by x gets closer and closer to 0. This number is going to get smaller and smaller. So what we'll do is we say that as x approaches infinity, 1 over x is going to get close to 0, 1 over x squared is going to get close to 0, 2 is going to stay there, 5 over x gets close to 0, and 3 over x squared is also going to get close to 0. So as x approaches infinity, this is what happens. So as x approaches infinity, as x gets bigger and bigger. So this becomes 0 over 2, which is equal to 0. So from this, we can conclude that as x gets bigger and bigger, our function gets closer and closer to 0. So since our function is getting closer and closer to that number 0, we're going to have a horizontal asymptote there. Okay. So going back to this definition here, we said that if our function approaches some number as x goes to infinity, then that line there will be a horizontal asymptote. Similarly, going back to our vertical asymptote here, we know that if our function gets bigger and bigger as x approaches some number, then that number is going to be a vertical asymptote. So we can look at this for example here. We know we're going to have a vertical asymptote at -3. So as x gets closer and closer to -3, so for example, if x were negative 2.99999, then our function is going to be negative 2.999 plus 1 over, this is a plus 1, 2 times negative 2.99999 squared plus 5 minus 3. Okay, and if we were to plug this into our calculator, we would get 28,571.37. Okay, and if we were to keep doing so, as this number gets bigger and bigger, so if we were to do 2.9999999, then this number would be bigger. So as we get super close to this number here, our function is getting very large, and so that satisfies this definition here for our vertical asymptote. All right, so let's look at another example here. We want to again find the domain and the asymptotes of this graph here. So right off the bat, we know that we're going to have a vertical asymptote at x is equal to positive 2, because if we were to plug in positive 2 into this function here, our function would be undefined. And this tells us that our domain then is going to be all real numbers except 2, since again 2 makes our function undefined. All right, now we want to find our horizontal asymptotes. So we're going to divide each term in our function by the variable of highest degree. So we're going to divide every term by x squared here. Doing so, we'll get 1 plus 1 over x squared on the top, and then 1 over x minus, oh, this should be over x squared here, minus 2 over x squared on the bottom. Okay. Using the same property that as x, when it's in the denominator like this, as x gets bigger and bigger, then this whole fraction here approaches 0, we'll get 1 minus 0 over 0 minus 0. Okay. We can't divide by 0, so this guy is going to be undefined. So we can conclude that as x gets bigger and bigger, or approaches infinity, f of x does not approach any real number. Okay, so we can conclude that we don't have a horizontal asymptote. Okay, and we'll see that this happens whenever the degree of the numerator is going to be greater than the degree of the denominator here. All right, and then something else to notice here. If we were to rewrite our function using synthetic division, we'll get the following. We have f of x is equal to, we started out with x squared plus 1 over x minus 2. And performing synthetic division, we'll get that our quotient is x plus 2 here, and then we'll have a remainder of 5. So this becomes x plus 2 plus 5 over x minus 2. And then something to notice here, we have this form where we have something in our numerator and x in our denominator here. So we know that as x gets bigger and bigger, this term here, 5 over x minus 2, gets close to 0. When this happens, our function is going to get closer and closer to just x plus 2 here, right? If this gets really close to 0, then our function is going to approach this here, which is just a line. All right, now notice this line here, x plus 2, is not horizontal or vertical. It's not a horizontal or vertical asymptote. It's actually called an oblique asymptote. So not horizontal or vertical. So we're going to have an oblique asymptote at y is equal to x plus 2. And then I have this graph here on the side of this function. As we see, we're going to have a vertical asymptote at x is equal to 2. That's what we saw here. And then we'll have an oblique asymptote, so one that is neither horizontal nor vertical at this line here, x plus 2. All right, so this brings us to our methods for determining asymptotes. So to find asymptotes of a rational function defined by a rational expression in lowest terms, we're going to use these procedures. So for the vertical asymptotes, we're going to set the denominator equal to 0 and solve for x. If a is a 0 of the denominator, but not the numerator, then the line x is equal to a is going to be our vertical asymptote. So a is the number that makes our function undefined. Now for other asymptotes, there are 3 possibilities here. If the numerator has a smaller degree than the denominator, then we can conclude that there's a horizontal asymptote at y is equal to 0. And so we saw that in the first example here. We see that the degree in the denominator is bigger than that in the numerator, and we got a horizontal asymptote at y is equal to 0. However, if the numerator and denominator have the same degree, and f is of this form here, this rational function form, then the horizontal asymptote is going to be the coefficients of our leading term in our numerator divided by the coefficient of the leading term in our denominator here. So I believe we'll see that in the next example. Then we'll see that if the numerator is of degree exactly 1 greater than that of the denominator, then there might be a oblique asymptote. And so to find it, we're going to divide the numerator by the denominator, so that's where synthetic division comes into play. And disregard any remainder, because as we saw, the remainder gets really close to 0. All right. Now here we have a 6-step procedure for graphing a rational function. So if we have a rational function expressed in lowest terms, these are the steps that we're going to follow to graph it. First, we're going to find the domain and vertical asymptotes, as well as any horizontal or oblique asymptotes. We're going to find both x and y intercepts. And then we want to determine whether the graph will intersect its non-vertical asymptote. We'll do so by solving f of x is equal to b is equal to that asymptote. And we'll see an example of that. Then what we'll do is plot any selected points as we need and complete the sketch. So we'll do an example of this here. So this function here was actually the first function that we saw, or this function that we saw in the first example. And there we saw that we had a vertical asymptote at x is equal to 1/2 and x is equal to -3. And so this told us that our domain is all real numbers except for those two. Right, so this was from first example. So we just set our denominator equal to 0 and solved for x. Similarly, from the first example, we saw that we had a horizontal asymptote at y is equal to 0. And we also know that this is the case because the degree in our denominator is bigger than the degree in our numerator. So using this here. All right, so for step 3, what we're going to want to do is find the y-intercept, and for step 4, we're going to find the x-intercept. So we know to find the y-intercept, all we have to do is set x equal to 0 into our function. So we'll end up with -1/3 here. And so this tells us we'll have a y-intercept at 0, comma, minus 1/3. On the other hand, if we want to find our x-intercept, we'll set our function equal to 0. And since we're dealing with a rational function, we know that this will only be equal to 0 when our numerator is equal to 0 and not our denominator. So, setting our numerator equal to 0, we can solve for x, and we get x is equal to -1. And so this tells us we'll have an x-intercept at -1, comma 0. Now for step 5, like I said, we want to figure out whether the graph will intersect its non-vertical asymptote. And we know that our non-vertical asymptote is y is equal to 0 here. So we're going to set f of x equal to 0 and solve and figure out if there are any x values that make our function equal to 0. We know that our function is going to intersect our horizontal asymptote when f of x is equal to our horizontal asymptote, so when it's equal to 0. And we actually saw from step 4 here, this guy will be equal to 0 if x is equal to -1. Right? Since we have a rational function, it can only be equal to 0 if our numerator is equal to 0. So we can conclude that our graph intersects our horizontal asymptote, or the x-axis, at our x-intercept, right? And that's to be expected. All right. So now with this information, what we can do is look at some test values in the different intervals of our domain. So our domain is split up into these 4 intervals based off of the numbers that make our function undefined, or in other words, based off of the lines for our vertical asymptotes here. So what we'll do is pick a test value in each of these intervals and figure out the sign of our function. So for example, in this interval here, picking -4, we found that our function was negative, so it must be below our x-axis. In this region, our function is going to be positive, so it's going to be above our x-axis. In this region, it's negative, so it'll be below our x-axis. And in this region, it's positive, so it would be above our x-axis. So this tells us the behavior of our graph in those regions. But the first thing that we're going to want to do is identify and plot our asymptotes as well as our x-intercepts. So we know we're going to have two vertical asymptotes, one at -3 right here, and another one at +1/2. So right about here. We also know we're going to have a horizontal asymptote here, so our x-axis, like this. We also know that we're going to have an x-axis at -1, 0, and our y-axis at 0, -1/3. So right about there. Now we're going to use the information in this graph here to sketch our graph. So we know in this region from -infinity up to this vertical asymptote here, our function is going to be negative and below the x-axis. So it's not going to cross this here, and it's not going to cross this vertical asymptote either. So our function is going to look like this here. Similarly, in this region, from -3 to -1, so right here in this interval, our function is going to be above our x-axis, so it's going to be in this region, and it also needs to cross these 2 points. And then we'll see in the next region, -1 to -1/2, from here to here, it will be below the x-axis. So the fact that it has to intersect these 2 points here makes sense. So our graph is going to look something like this here, never crossing our vertical asymptotes. And lastly, we know in this interval, this region here, from 1/2 all the way to +infinity, our function is going to be above our x-axis, never crossing our horizontal or vertical asymptote there. All right, so that is the graph for our function here. All right, so the last example we're going to look at is this function here. But we need to be careful with this guy. If you remember, our procedure for graphing rational functions as well as determining our asymptotes only holds for a rational function that is in lowest terms. Now, looking at this function here, this guy actually is not in lowest terms. This is because, so I'll write that here. This is because we can rewrite our function as the following. By factoring both the numerator and the denominator, we'll get x plus 1 times 2x plus 1 on the top. And on the bottom, we have x plus 1 times x minus 3. Now, when factoring this, we can see easily that these guys cancel, and our function becomes 2x plus 1 over x minus 3. And now this guy is in lowest terms. We can't simplify it any further. All right, so now we're good to move forward in our procedure. So I'll list everything that we know. First, we want to find our vertical and horizontal asymptotes as well as our domain. So we can easily see that we're going to have a vertical asymptote at +3 here, because if x is equal to 3, then this guy is 0, and we know we can't divide by 0. So we're going to have a vertical asymptote at x is equal to 3, and then this tells us that our domain is going to be all real numbers except for 3. Now for our horizontal asymptote, we have 2x plus 1 over x minus 3, and we saw from our procedure here for determining asymptotes that if the numerator and denominator have the same degree, then our horizontal asymptote is going to be the line here, which is the coefficient of our leading term in our numerator divided by the coefficient of our leading term in our denominator. And looking back at this guy, we do in fact have that the numerator and denominator have the same degree. So our horizontal asymptote is going to be the line y is equal to the coefficient of the leading term in our numerator, so that's 2, over the coefficient of the leading term in our denominator, so that's 1. So we're going to have a horizontal asymptote at y is equal to 2. All right. Now we want to find our x and y intercepts. So setting x equal to 0 in our function, what we'll get is negative 1/3. And so this tells us we're going to have a y-intercept at 0, minus 1/3. And on the other hand, setting our function equal to 0 and solving, we'll find our x-intercept. And we know that this guy, our function, is going to be equal to 0 only when our numerator is equal to 0. So we'll just set that guy equal to 0. Solving for x, we'll get x is equal to minus 1/2. And so this tells us we're going to have an x-intercept at minus 1/2, 0. All right. Now for our next step, step 5 from our procedure, what we want to do is figure out if our function is going to intersect our horizontal asymptote. And we'll do so by setting our function equal to our horizontal asymptote and solving. So we're going to set our function equal to this guy and solving. Now, what we'll do is we have 2x plus 1, and we'll multiply by x minus 3 on both sides to get rid of that fraction. So we have that there. Then we'll get 2x minus 6 on the right-hand side, just distributing this 2 to both terms here. Then we'll see we have 2x on this side and 2x on the right-hand side. So if I were to move this 2x to this side, I would just get 2x minus 2x, which is 0. I would be left with 1 is equal to minus 6. And that is not a true statement. 1 is not equal to minus 6. So this tells us that this guy has no solution. And therefore, our function will not intersect our horizontal asymptote. All right, and then step 6 from our procedure is to plot up a couple points here. So I've done that already. And so now we have all of the information that we need to graph this guy. So first, we will plot our asymptotes as well as our x and y intercepts. So we know we're going to have a horizontal asymptote at y is equal to 2. Then we have a vertical asymptote at x is equal to 1/2 here. We also know that we're going to have a y-intercept at 0, minus 1/3. So that'll be somewhere around here. And an x-intercept at minus 1/2, 0. So somewhere around there. All right. Picking a test number, minus 4 here, we get our output is going to be 1. So it's going to be above the x-axis, and it's going to be right about there. All right. Similarly, plugging in 2 into our function, we get minus 5. So in that region, our function is going to be below the x-axis. It's negative. So it'll be right about there. So this tells us that our function in this region is going to look something like this here, never crossing our horizontal and vertical asymptotes. Similarly, in this region here, plugging in some test numbers, we'll see that our function is going to be above the x-axis. Plugging in 4, we get 9, so somewhere right about there. And then plugging in 8, we get about 3.4, so maybe somewhere around there. So this tells us the graph in this region is going to look, do that a little better, something like this here, never crossing our vertical or horizontal asymptotes there.